Okay, so here we go. So let's do so let's call shaft design stresses. Okay, so because a shaft let's say a power shaft rotates in time, the classic failure criteria methods cannot be used. So for example, for static, okay, so static loading, generally, what was the criteria? Okay, we might do a little bit of this later on anyway, but what is the general criteria is, let's say if you have, let's just talk about bending. If you have the stress strain curve, so generally we'll have this shape for a general elastic material. So let's see, the slope of this line is what is the Young's modulus, all right? So if the material is brittle material, let's think about glass. When is a glass going to break? It's either in good shape or is broken, no? There's nothing in between. So basically what means there is no deformation, okay? So it will break probably at one value along this line. Yeah, okay? So that would be brittle material will break at just one value, okay? Let's say whatever, here. Then if you have an elastic material, think more about a metal, what's gonna happen? You start and think that you are stretch it. What's gonna happen? You stretch it, it's gonna move. So as you increase the force, the wire is gonna deform. Then as soon as you get a certain value, what's gonna happen is that you keep increasing the force. So without increasing the force, it's gonna keep increasing. And then generally around this area here, it will break. Okay, so this would be about brittle. And this would be the elastic. Okay, so if you want brittle material will break, so failure at lower or equal than sigma elastic, that will be this value here. And this one will be lower or equal to sigma plastic, that will be this one here. Okay, so we're going to look at two cases. Oh, okay, multiple cases. So let's say shaft in bending and torsion. And this is generally known as fluctuating load. Okay, so what do I mean about fluctuating load? I'll do a simple case. So fluctuating basically means that it's going to go between a maximum value and a minimum value. So if we look at shear, this, right, if we look at the cross section of the beam, or the shaft, sorry. Okay, so you will have, even though you calculate the shear to be constant, because the load would be fluctuating, you're gonna have to consider maximum and minimum value. Okay, well, tau over here would be equal to TR over J. Okay, so I'm just gonna put now 2 sentences. All right, so the most common stress situation encountered for a transmission shaft is to have reverse bending and let's say nearly steady state torsional stress. Okay, and let's say the least common stress situation encountered is, so we're still gonna have reverse bending. This is always gonna happen. And reverse torsional, so reverse bending stress and stressoid. Okay, so what does that mean? This sounds kind of complicated, but then the equations are going to be a lot easier. The important term over here to understand is fluctuating. So if they are fluctuating, they will be fluctuating between two values, no? Okay? So what you need to understand here is this. Okay, so let's say, let's consider a general element. So what I'm trying to say over here is just imagine that you have your shaft over here that can be subjected to all kinds of loads. All right, I made them up, okay, doesn't matter. But let's say we're gonna look at one element over here. So if we look at that element over here, that element, and let's say there's a torque over here, okay? Doesn't matter, whatever you want. So that element is going to be subjected to what? It's going to be subjected to normal stresses and shear stresses. So let's say it's subjected to a normal stress and is subjected to a shear stress. Okay, doesn't matter, whatever you want to call it. Okay, so what's important to realize is that the total stress will have a static component that will be there all the time, plus I like to call it dynamic, but generally in structure, they call it fluctuating component. So we can have over here sigma x will be equal to the static component. That will be the average stress. This will be the static component plus a fluctuating component that will be equal to, let's just call it sigma sub r times a, if there's any change in geometry, there's a key, a round of age, whatever you want, it will be a stress concentration factor. And now this needs to be multiplied by stress yield point divided by the endurance stress. I'll tell you what that is now, okay? And similarly for shear, you have that the total shear stress would be equal to a static component plus a fluctuating or dynamic. So it's exactly the same notation. I'm going to follow the same steps. Average plus tau sub r, k sub t, s y p over s endurance. Okay, so I don't know if it's a good example or not, but let's say somebody is shaking your hand. So it's always going to be a static load because the person will be holding your hand, no? And now imagine the person start moving up and down the hand, this will create an additional load. Okay, so you can break it into the two components. All right, so in this equation, we say that K of T will be the stress concentration factor due to any irregularity on the geometry. S YP is stress at yield point, and S sub E is the endurance stress, which is the maximum stress before failure. So basically, I mean, the SYP let's say you have here loading. So let's say force times here, let's say SYP. This journey will be, it's the same figure that I did before. You want, let's put the same as before. This will be stress. This will be deformation. That will be easier. So what is the yield point? The yield point will be the value where the stress relation. So I hope you remember this from solid mechanics. How do you obtain this curve? You do the ASTM testing, no? And gives you sigma equal E over epsilon, no? Okay, so this is like having Y equal AX. This is a linear function. So at the point when it starts being linear, that is what is known as the yield point. Okay, now imagine that you have a piece of metal and somebody is going to start doing like this. So they're going to have now they're going to have the stress over here in function of time. And they're going to find out that, let's say, in function of time, when is this going to fail? And they have a curve, whatever. So let's see. How should the curve look like? So the higher the initial stress, the sooner it's going to fail, no? The lower the value will be lower the value. But this should be all experimental data, right? That is obtained. Okay, so I'm going to put over here something that I don't expect you to understand what is coming. This is more complicated to derive it, which I'm not going to derive. But let's say for elastic materials, the von Mises stresses are generally considered. Okay, and this is, if you look at, let's see over here. I mean, if you look to any finite element, I don't know if I have here a program to open, file, open. I think we all have, All right, let me go to something else here. ME400, so let's see back here. See if I have something here. Okay, let's say this one here. I don't know if I'm done it or not, hopefully. But basically, if you go to any type of problem, you will see you have different, you have different stresses, but you have shear stresses, but then you're always gonna have von Mises over here. Okay, and von Mises for any material that is elastic, basically that can deform, everybody will use von Mises. Okay, so even the final element over here will give you the output. And the way it's obtained, I'm gonna kind of mention it, but I'm not gonna do it. Okay, that comes from the theory of elasticity, which is not a big deal. So basically what's gonna happen is that you say that the stress in one direction square is this value of 3 equals 3 tau xy square for failure, and this value, when you add these two stresses, they need to be equal less to the stress at the yield point divided by NSF, which is a safety factor square. So over here, you say NSF is safety factor. So basically, what is a safety factor? Let's say that you do the design of a beam, you do all your calculations, but then at the end you say, you know what? This is my calculation. I estimate that the minimum, let's say, height of the beam needs to be for the I-beam. We're going to use that I-beam like you did on the exam. But you know what? I don't know how good the material is going to be. I don't know how good the workers are going to build this bridge, no, or this beam. I don't know if then maybe the properties are going to change in function of time. They're not going to be new all their life. But I want this to last at least 20 years. So I'm going to be safe. And that's what basically civil engineers do. I mean, civil engineers, do they care about the weight? They don't care. So sometimes they take safety factors of 10 or 20, okay? If you design an aircraft, is it important to be careful with the weight in an aircraft? So they will take safety factor a lot smaller, no? So that's when you need to be a lot more accurate. But let's say you decide to take a safety factor of 2 or 3 or 4, all right? So then everything will change, no? Okay. All right, so now what I'm gonna do, I'm just gonna rewrite this expression here, like we did over here, all right? I'm gonna substitute each one of these values here. So this is not tau x, this is to be tau xy. This is shear. So I'm just substitute those values into the above equation. So substituting previous equations, and maybe we can give them names. It will be easier. So let's say it will be 1 and 2. So Roman 1, Roman 2. Into, let's say, A. And we call this one here A. What do you get? So you're going to get sigma average plus sigma sub r k sub t as yield point divided by the endurance stress, everything square plus 3 times the average shear plus tau sub r k sub t s y p over s endurance, everything squared needs to be lower or equal to P over safety factor, everything squared. Okay, so this is the general equation for the stress design of a shaft. Okay, so this is a general equation. All right, so on the previous page or on page 89, what do we say? The most common situation encountered is when there is reverse bending and nearly steady state torsional stress. Okay, so what we're going to do over here is, let's say, case one, let's call it case one, will be reverse bending, as we said before. Plus nearly constant state torsional stress basically mean static torque. Okay, so in a problem, they give you this information. What does it mean? So let's see. If there is reverse bending, let's see, what is that figure? So basically, this is the fluctuating, this is the reverse due to the fluctuating part of the load. This is the static, okay? And we have the same thing over here, static and fluctuating or fluctuating dynamic. So on reverse bending, basically, what are we assuming? We'll be assuming that the static normal load will be 0. So this will mean that sigma average is 0. And if you assume static torque, what's that going to mean? That the term due to the fluctuating stresses will be the second one. This one will be 0. So let's say tau little sub r will be equal to 0. So let's call this equation here B. So you say in that case, comma, equation B simplifies to so to what? Sigma sub r k sub t s y p divided by s sub e, everything squared, plus 3 times the average shear stress. And this should be also square, lower than SYP over safety factor. Okay, so you will have this. Okay, I'm gonna do, it's not like an, yeah, this is a general notation, okay? Let's over here, special case. This is just for the understanding. Let's say that the safety factor for equal to 1 and I'm going to change the notation and let's say sigma sub r k sub t equal to S sub b. So it's bending stress basically. Okay, I'm going to substitute into the above equation. So this equation becomes what? This becomes S of b S yp over S of e. All this stuff is not important. The only thing important is the figure at the end. Square plus 3 times the average stress square would be equal to the yield point stress square. You see, I do it in green just to show that this is important equation, okay? This is just a special case. So dividing both sides by S yield point square, what are you gonna get? You're gonna get that S sub b divided by S sub e square plus 3 tau average divided by S yp square would be lower than 1. Okay, so I'm not going to go to the next page. So if you think about mathematics, let's say this is x, this is y. What is x squared plus y squared is the equation of what? Of a circle, okay? So basically what's going to happen is that if you plot the data this way, so let's say you have S sub b over S sub e versus the tau average over S sub yp. This should give you some type of curve. I mean, it's not going to be a circle because there's a 3, but it should be some type of ellipse, where this will be here 1 and 1. And basically, so you do this figure, what is that going to show is that if you are under the curve, your structure will be safe. And if it's outside the curve, your structure will fail. Okay, so you can do the same plot. You see, if you have the data, you can do some type of the same plot, no? And that's what it's meaning. But again, this is just a special case. I just wanted to do the figure here to show you that this is 1. So the radius would be 1 and so on and so on. Okay, so similarly, we did the least common case is when you have reverse bending and reverse torsional stress. So that means that you're gonna have both fluctuating loads. So for case 2, So case 2, I'm gonna write reverse bending plus reverse torque. So if you have this, what does that mean? That both static parts of the loading will be 0. Okay, and I can just follow the same procedure as before in that case. Equation B becomes, so what would be the equation? Would be this one here, where you would take this term equal to 0 and this term equal to 0, okay? So you have sigma sub r k sub t s yield point over s endurance, everything squared plus 3 times d tau sub r k sub t s y p over s endurance, everything squared equal lower than s y p over n safety factor squared. Okay, so the reason that I give you these two cases is because these are the most common cases that you might have to study, you find in an exam, but on an exam, I mean on a problem. But let's say on an exam, I can give you a different case, no? I mean, you have different combinations. You can have, for example, let's say if it's only static, then you could eliminate this term and this term, no? And this would be like solving a static problem. You could have whatever, you could have this one not being equal to 0, but this one being equal to 0. This one equal to 0, but not this one. Okay, you have different combinations, no? Okay, but the equation is always the same. All right, and always, no matter what, after the calculation, you might end up with one of these curves over here. So let's start working on a problem. I don't know if we will have time to finish it up or not, but let's just work on it. So example. All right, so a revolving shaft carries a bending moment of 27,000 inch per pound. And a torque of 80,000 inch pounds. Assume that the torque fluctuates %20 each way from the mean value. If the stress concentration factor for bending and torsion is 1.35. Determine if the design is safe for, so let's see, I'm not going to write everything, for a yield stress for SYP equal to 90,000. It should be PSI. And endurance stress of 44,000. A safety factor of 2.5. And the shaft has a diameter and a diameter of 3.375 inches. Okay, so all this is a lot of writing, and I'm not good at reading. So what I like to do, I wanted to translate everything into some type of figure. So let's do a figure, okay? So if I needed to do a figure for this problem, let's say you do some type of shaft over here. We know this is the shaft. We know it's a solid shaft. Over here, for which, what do we know? The diameter is 3.375 inches. What else do we know? This one will be subjected to a bending moment. So let's say some type of bending moment. Okay, bending moment, you have a moment of 27,000 inch B. What else do we have? We have a torque of 80,000 inch LB. And we know that it fluctuates 40%. Okay, so you have to give me values because I don't think I have all the calculations. So And let's say, and this one fluctuates 20%. Okay, so again, if we look at one small element over here of the beam, that little small element will be subjected to normal stresses and shear stresses. So let's say if we look at normal stresses first, or bending stresses, let's call them bending stresses. It would be easier. Bending stresses. Or bending stress. So what should be the equation? Should be sigma equal to my over I. Oh, maybe I should have solved for the I over here. So let me give you those values. Sorry for that, maybe I should have put it here. So the I over here is equal to pi divided by 64 diameter to the 4. And if I didn't do a mistake, this is equal to 6.3688908 inches to the 4th. The J equal to the I sub P is basically equal to pi over 32. So twice the other one, D to the 4th. And this will give you 12.73782 inches to the 4th. Okay, so if we do the calculation for this one I have it, but I'm not gonna have the next one. So this will be equal to what? 27,000. What would be the Y? Should be the radius, no? Half the diameter, correct? Yeah? I don't need to do the figure, no? So we have here, this would be the neutral axis. This would be the Y, no? Yeah, for bending. So this will be D over 2, which is 3.375 divided by 2. Everything divided by 6.368908. And if I didn't do any mistake, this will give you that sigma x over here on the equations. Sigma x. This one will be equal to sigma sub r, which will be equal to 7,154 PSI. Okay. Now we're going to look at the shear stress. Or shear stresses. To follow the same notation. So shear stress we know will be tau xy will be equals to T times R divided by J. So this will give us what? Is 80,000 times 3.375 divided by 2 divided by the J that we say is equal to 12.73782. And this gives you a tau XY equal to 10,598 PSI. Okay, but here is where I'm going to need your help because I didn't do the calculation. What do they tell us of the problem? Assume that the torque fluctuates 20%. Okay, so either we have the choice to multiply the 80 by 1.2, no, to get the extra 20%, or over here we can say, so torque, 20% fluctuation of torque. So it means what? That the tau sub r we're gonna put will be equal to 1.2 times the tau xy. So what is this value, please? It should be 12 or 13,000 something, I don't know, 12,000 something.
12,707.6.
So 17, 18, okay. So we keep it simple. I mean, the same thing that is important to be accurate for the moment equations, not to round off because that can create issues for the deflection curve. For stresses, go ahead and always round off high, no? Okay, it's not gonna hurt anything, okay? So you need to be careful. So really this will be 20% higher. Okay, so let's say, let us recall the equation, which is the one of the design. I think we call it equation D. So this long equation over here, okay? So equation B. And let's see what is the case in this problem. So we have sigma average plus sigma sub r, k sub t, syp over se, everything squared plus 3 times tau average plus tau sub r, k sub t, syp over s sub e, everything squared, lower or equal to s yp over safety factor, everything squared. Okay, so here is where we need to be careful. So here is not a correct answer, not correct answer. If you want, depends on your assumption. But if we read this problem, a revolving shaft carries a bending moment of 27,000. So what does that mean? Do we have a static load for bending or just the dynamic, the fluctuating? Looks like they're just giving us the fluctuating, no? All right. So in that case, you could say, in this problem, you have the static value, which would be the average, would be equal to 0. And now, so this will be our average. Let's say this will be also, this would be the average. So basically, maybe if I should have done here a figure, maybe we have some space over here to do the figure. Here you have the average stress, and then you have the fluctuating stress, would be the tau sub R, which is 20% higher. Okay. Okay, so basically the only thing we have is in this equation, this will be equal to 0. All right, so for above equation, we have this one equal to 0. We have sigma sub R to be equal to what? 7,154. Now, K sub T, the problem say to assume 1.35 for both bending and torsion. Then we have, okay, let me go with this one, the tau average will be equal to 10,598. The fluctuating shear will be equal to 12,718. The safety factor in this problem, they said to be equal to 2.5. And what else? The stress yield point was given to us to be equal to 90,000. And the endurance stress to be equal to 44,000. Okay, so if you substitute all these values, and here I can show you the MATLAB file. Maybe I can find it. Let me pause this for a second. So here I have a MATLAB file to do the calculation. C27, 80,000, 2.5 K sub T. This is just because I think what's going to happen is that it's going to be unsafe. So we're going to have to run different cases for different diameters. And this is run cases from 3.375 to 5 and break it into 20 in between, okay? That's what this means. The I is given over here, pi over 64. The J is twice that one, Sy of P. And here you see the tau sub R. I multiplied this one by 1.2, which is the extra 20%. And this should give you the values over here, okay? So, I don't know what's gonna change this, but anyway, if we follow this MATLAB file that I might just add to the class notes if you want, what this is going to give, so if you substitute into this equation here, you get that, so substituting into above equation, meaning this one over here, you get that 6.6605 10 to the 9. In order to be safe, should be lower or equal to 1.30 10 to the 9, which actually what happened? This is not true, no? This is not satisfied. So what does that mean? That design not safe. Okay, so now if it's not safe, all right, so next, since the initial design fails, let us determine a shaft diameter that makes it safe. Okay, so here there is two ways to do it, right? One would be, let's say, the numerical that we have over here, which basically I think I do like different values. No? All right, for D, you see this means that D, what is it? The value of D will start at 3.375, will go all the way up to 5. I don't know how to minimize this stuff here. So let's see, this is for what? So this looks like for 3.6. What do we need to have? We need to have the left-hand side lower than the right-hand side, no? So 3.6 doesn't go, left-hand side lower than right-hand side. Okay, let's keep going for a while. Okay, so it started getting closer here. So you see here, I have an argument saying safe, no safe. I mean, I can go right away, safe. So here, first one safe, no safe. So it looks like once you reach the diameter 4.4868, okay, the left-hand side is lower than the right-hand side. And this will give you that D equal 5724, okay? So let's just write it down. Using MATLAB code, the minimum diameter is 4.5724. No, 4468, I guess. I don't know which one is. So I don't know if it's the before or the end, but safe or no safe. I'm guessing it's 4868. Okay. 4.4868. Is that you could use basically Maple to do it for you, okay? Instead of doing a program and do the iteration all the time, you could just put the values, you write down the equation for every single term, and at the end you just say to Maple solve for the for D, and it will give it to you. All right, and here all the solutions are imaginary except for the first one. So if you did it this way, you get 4.433, and the other way we got a solution to 4.4868. Okay.